In 1941, a Swiss engineer pulled burrs off his dog and stumbled onto one of the most versatile fasteners ever made. From spacecraft to surgical tables, the story behind how Velcro actually works starts under a microscope. That engineer was Georges de Mestral. Returning from his alpine hike, he wanted to know why those persistent burdock burrs clung so tightly to his wool trousers. Zooming in under the lens, he discovered that the burr's surface was covered in thousands of rigid, microscopic, J-shaped hooks. They caught perfectly on the tiny loops of his clothing. By copying this natural hook and loop pattern, a classic example of biomimicry, he spent years working to replicate it synthetically. He named his invention Velcro, blending the French words for velvet, velour, and hook, crochet. At its core, this system relies on two completely different surfaces working in perfect harmony. One strip is the hook side, a rough, rigid texture bristling with thousands of tiny, microscopic J-shaped plastic hooks. The other strip is the loop side, covered in a soft, fuzzy forest of flexible yarn loops. When you press these two complementary surfaces together, something incredible happens at the microscopic level. The stiff plastic hooks slide easily into the pliable fabric loops, catching and securing them in thousands of tiny mechanical interlocks. Because this connection is purely physical, it completely bypasses the need for sticky chemical adhesives, which eventually dry out, lose their tack, or collect dirt. Instead, simple mechanical friction keeps the strips firmly locked in place. Pulling the fastener apart at a sharp angle simply causes the flexible polymer hooks to bend, safely releasing their grip on the loops. The hooks then spring right back to their original shape, undamaged and ready to latch on again for thousands of cycles. Modern hook and loop fasteners are highly customizable engineered products designed by manipulating physical chemistry and structural layout. Standard versions rely on synthetic polymers like nylon and polyester. For light-duty consumer uses, manufacturers weave classic textile tapes with soft, pliable loops. Heavy-duty jobs, however, require molded hooks. Liquid plastic is injection molded to create stiff, precise arrays of J-hooks or mushroom heads. By adjusting the hook density, which ranges from 5,000 to 12,000 hooks per square centimeter, designers scale up the holding strength. The height and texture of the loop pile are also calibrated to change how quickly hooks catch. Finally, adding heavy-duty adhesive to the backing creates peel and stick mounting systems, turning a simple fabric strip into a structural tool. Force direction completely changes how this fastener behaves. When pulled sideways in shear, the sliding resistance is remarkably high because thousands of contact points stay engaged at the same time. You can easily see this strength by hanging a heavy weight from a joined strip. It refuses to budge. But try lifting that same strip from a single edge, and a slow, gentle pull peels it open. This peeling action concentrates the entire load along a narrow front, releasing the hooks one by one with minimal effort. This directional behavior offers adjustability and simplicity that traditional zippers and snaps cannot match, even if those classic closures offer a slightly tidier look. Grip strength also depends on hook shape and design density. Specialty shapes like mushroom heads grip tighter than standard J-hooks, but every version eventually faces physical limits. Debris like lint and pet hair quickly clogs the loops, cutting holding power by 40%. Outdoor ultraviolet rays and extreme temperatures degrade the polymers over time, while thousands of opening cycles gradually wear down the hook shapes themselves. Step inside the International Space Station and you'll find hook and loop everywhere, keeping tools, food trays, and sleeping bags from floating away in microgravity. Back on Earth, it is just as vital. Camera crews use it to bundle chaotic nests of cables on fast-paced sets, while military MOLLE systems rely on heavy-duty strips to swap out gear pouches instantly in the field. Even in high-tech labs, engineers slap temporary Velcro patches onto robotic arms to quickly position sensors and test modular prototypes. It is the ultimate tool for a world that needs to stay organized, modular, and fast. In hospitals and rehabilitation clinics, hook and loop fasteners secure orthopedic braces, allowing patients to adjust compression instantly without any tools. On Broadway, these exact same strips enable 5-second costume quick changes and hold lightweight scenery panels silently during a performance. Even curators at the Smithsonian and the Louvre rely on low-impact loops to mount priceless artifacts reversibly, avoiding the need for destructive nails or adhesives. And in adaptive sports, easy closures on prosthetics and wheelchair gear give athletes the independence to secure their equipment and fine-tune their fit on the fly. Next time you hear that satisfying rip, remember, nature's simplest designs still hold our world together. What everyday wonder should we explore next? Let us know below.